Good evening, everyone, or good afternoon, depending on what part of the world you're joining us from. My name is Sam Nasser, and this is the Azure Cleveland User Group. A little bit about the group. We meet every month, typically every second week. The meetings are free of charge and open to the public, and we cover a variety of topics related to Azure. You can find all the meeting information posted on meetup.com at the link listed at the bottom of the slide. We'd always like to give a big thank you to our sponsors, the .NET Foundation for sponsoring the Meetup website, as well as NIS Technologies for sponsoring the virtual meeting space, as well as the recording. Some general information, if you're joining us for the first time, please keep in mind participation is encouraged. This is intended to be a knowledge sharing session. And like I always say, the only stupid question is the one not being asked. So feel free to jump in with a question or a comment, either verbally or in chat. However, when not speaking, kindly ask you to mute your microphones just to avoid any background noise. And we want to keep it casual but organized, meaning feel free to chime in, but at the same time, we want to give our speaker enough time to go through the presentation and the demos. And the presentation is being recorded and will be posted on YouTube. The link for that will be posted in the chat window shortly after the meeting. So for tonight's presentation, we have built a goal-oriented AI agent using Semantic Kernel. This is by Bill Wilder. Bill is a seasoned AI consultant. He's also worked in various capacities in software architecture, Azure, and cybersecurity. And he's also the founder of Azure AI in Boston. And in addition, he's a Microsoft MVP, and he is CI SSPP certified. So with that, glad to have you joining us, Bill. Welcome.
Thank you, Sam, for inviting me here, and welcome everybody. This session is going to be a combination of some slides and a few demos, a couple short demos. And it's okay to interrupt if you, well, we can try that. You can feel free to come off mute and interrupt because it's a small group, so that usually works okay. I'll periodically try and glance at the chat too if there's a question posted there. Let's see. So Sam introduced me. So just one interesting thing, I have been like you all, I've been involved with a community group called Boston Azure that I started a little more than 15 years ago, and then since AI took over so much of the attention in our community, most of our talks, and in the industry, recently we rebranded as Boston Azure AI. So you can find us there. We also, like you, we have meetings sometimes in the evenings where you can join remotely if you wish. Let me start with a brief history of artificial intelligence, very brief. The term was coined in the 1950s. There was a meeting of some academics. John McCarthy, I think it was the person who coined it. And then I'm going to say a little bit tongue-in-cheek, but I think this is mostly true from a commercial and impact point of view, where we went for about half of a century with not a lot of progress visible to civilians. You know, the AI community had some good stuff going on occasionally, but nothing that broke through and seemed to suggest a shift in the way we live our lives. In the early 2000s, there was a shift. The first half century or so of AI was a lot of it was done in the programming language Lisp or its dialogue scheme. Same guy who coined the term AI, John McCarthy, also created Lisp back in the late 50s. We had expert systems, and that's the last prior century, and then that yielded to from things that were based on languages and hand-coded rules and so forth, Lisp, think expert systems maybe, that yielded to a new paradigm which is based on large volumes of data, and that's machine learning. Machine learning is a subset of AI. So if you look at the big picture of AI, one piece of it is machine learning. And within that, we have what we now think of as AI today, which is the large language model and generative AI. And of course, ChatGPT popped in late 2022 and changed everything. This is just a visual of the prior. So we have traditional AI that's been around for quite some time. Machine learning is a subset. Then Gen AI and LLMs are a subset of that. So just pointing out, like this is, we're in a little piece of AI that's taken over all of the oxygen about AI in the world, because we struck gold. I'm going to frame this conversation a little bit. It's not critical, but just I'm going to give samples and demos in a library called Semantic Kernel. There are multiple ways of interacting with AIs, and this happens to be a software development kit, an open source software development kit from Microsoft, and it's partly a more portable and more flexible toolbox to interact with an LLM because it's not tied to a particular vendor. So you can use Semantic Kernel to talk to OpenAI directly, not going through Azure OpenAI. You can use Semantic Kernel to talk to models that are OpenAI models that are hosted in Azure. So those are two. They have two different communication, connection models. They take different information and so forth to connect to the API. You can also talk to Gemini from Google or Claude from Anthropic and Llama from Facebook and so forth. These are all available through Semantic Kernel. So it's a more general toolbox. We're going to talk about the tool support that Semantic Kernel supports. Semantic Kernel, like every other SDK these days, supports chatbot style interfaces, and we'll talk a little bit about that. And we will very lightly touch on some of these other topics like RAG, vectors, and agent we'll focus a little more on because we want to leave you by the end of this conversation with an understanding of the most critical difference between a chatbot and an agent. So the chatbot is if you go to ChatGPT or Copilot or any of the many available LLMs out there that have a web interface or a little app on your browser, and that's usually a chat experience. Who's going to win the Super Bowl, or tell me about ancient Rome, and it gives you a chat experience. An agent is somewhat different from that, and we'll talk about that. There's a couple of URLs here. One is the Semantic Kernel NuGet package, and the other is the Semantic Kernel repo, open source repo. Semantic Kernel, just to give you a little further background, it started out as a somebody told me this. It started out as in the office of the CTO at Microsoft, so it was not like a product at that point. And it started in, I think, January of 2023 or maybe February. And it, very shortly after ChatGPT popped. And the goal is to give 3 sets of language bindings. You're going to find that most SDKs favor Python. The Semantic Kernel has 3 co-equal branches of government. One is for .NET, and then it's Python and Java. And they've actually moved on from 1.0 at this point. But the point of this slide is that there are 3 paths. So whether you're Python, .NET, or Java, and think about .NET and Java, or C# and Java, as the enterprise solutions. I don't think it's going to be practical for a lot of enterprises to shift a lot of their development to Python. There's no reason to do that. If you're building an LLM, you probably want Python. But if you're consuming an LLM, like 97% of the use cases will be, then you should be able to use the languages that your teams are familiar with on the platforms that you already have your enterprise app built in. 1 billion served. They reached that milestone in the fall, where they're this is their enterprise scale solution. This is what Microsoft advises you to use for enterprise scale solutions that you code. I talked about this a little bit. Python is the language for ML and AI modeling, but Sovereign, C# and Java are really enterprise software languages. So just emphasizing that point. And you'll find when you use the semantic kernel approach, it allows you to get the best of the ecosystem. You have you can write your again lower learning curve for your development teams. You can build stuff in idiomatic.net or Java or Python if that's your thing. You can integrate with other great .NET stuff. Dependency injection is a first-class citizen. Aspire, the .NET toolset. OTel, the open telemetry stuff, is very well supported in .NET and semantic kernel generally. And like I said earlier, pretty much, pick out an LLM. You can connect to it with semantic kernel. So the last bullet is probably the highlight here. The takeaway. Semantic kernel reduces your incentive to leave C or Java. I'll also point out that we'll look at some code. We won't go super deep into the code, but I'll point out some code. And in a C# application, which we'll focus on, there are about 10 meaningful lines of code. I'm going to show you a sample app that has some other cruft in it, but the business work here is there's about 10 lines of code needed to interface with an AI service. So this is not super complex stuff. Okay, so it's just a little background. And then as I roll through the talk, I'm going to go through six topics. We'll talk about LLMs, tokens, embeddings, which I think is a really fascinating topic and probably deserves its own talk. Prompts, which is the angle most of you have interfaced to LLMs with the chatbots, and you've heard about prompt engineering and such. The tools is the key insight in the evolution from making something a prompt experience to getting to a full agent experience, and we'll dig into that more completely. All right. Again, it's okay to come off mute if you have a question or you don't, whatever, and we'll pick it up if you do that. Let's get into first key concept, which is the LLM. This is AI, big AI from the 1950s. A subset of that is machine learning, and a subset of that is some generative AI stuff that is basically based on the fact that we have this vast amount of data that we can train on: the internet, Wikipedia, Reddit, Twitter, books, all this in YouTube, all the stuff that was available for training made this large language model possible. A large language model is it's basically an AI model that you can connect to. If you go to Azure or another host, you can fiddle in the portal and say, create me a chat GPT 4.0 model, and that in the Azure platform in this case, for example, will give you back an API key, a model name, and a URL, an endpoint. And you can use those through semantic kernel or whatever, REST or other means to interface with the large language model. A large language model is stateless. So we'll talk in a minute or so about how can you have a chat with it if it's stateless. It's typically it behaves in a mostly non-deterministic way, and then we'll look at a couple of parameters that can accompany a prompt. These are temperature and top P that try to make it more predictable. And then we'll see that at the core, it's with all this stuff accounted for, you're programmatically hitting your LLM. You've given it some context. You've said, you've asked it a question, or you've asked it to do something for you. Write me a poem about the Azure Cleveland group, and it will, but it does it one token at a time. And we'll talk about what a token is in the next section. But at its root, it's a very simple machine. Here's some context. Write me a poem about Azure Cleveland, and then it returns a response that it generated one token at a time. Just for completeness, we usually talk about LLMs. There's another flavor called a small language model. And it's a simpler, less complex, trained on less data, and runs with less memory and ceremony. I don't think you could run the current ChatGPT models on your laptop, for example, but you can run, and you do run, some of you, small language models on your laptop. This is, you can even run them on your phone. So they're intentionally designed to be, usually they're more focused and not as general as large language models. But as an example, Microsoft has the Phi 4 just came out actually, and I've run that with no trouble on my of a MacBook Air that I'm demoing from, that I'm presenting from. And one of the tools that you might use to run an SLM is Olama. It's an open source tool, it's like running a Docker container. Very similar experience. You can download a model, might be some gigabytes, and you run a server on your local machine, and then you can you can tell it which model you want to run, and it'll give you a chat experience or program. You can talk to it locally through Semantic Kernel too, but it gives you that experience, except under your laptop's power and control. In the server space, this is Azure AI Foundry, models as a service host. I don't know that that's an official acronym, but there are a lot of models available up there, and there's a whole model catalog that you can dig into. In any of these, you can tell it to host, and you can run via API. You can hit the models. I will point out that the LLM space has different kinds of models that are visible on this screenshot. Most of them say chat completion, and that's the experience you get if you go to your typical web browser. Other ones are more specialized. This is a text to speech, text to image, and we'll dig into this just a little bit more a little later. There are also embedding models. So this is a model that tries to semantically understand text and convert it and store that semantics as vectors. And they have very interesting properties, like you could compare the semantics of two words or phrases. So you see there's many different kinds of models here, not just the chat ones. And no AI talking about LLMs would be complete without at least mentioning that the big AI players, they all have in place some sort of responsible AI. They call it different things. Microsoft calls theirs responsible AI principles. And these are principles that are designed to make sure that that AI, we don't get to Skynet and bad things happen. So if you try to do something irresponsible, according to these principles, with AI, the AI platforms might try to stop you from doing that. And I'll give a very trivial demo of that in a minute. And they have some things they can enforce, like that might be a safety thing, that you're asking the AI to do something that the AI really doesn't want to do for you. There are also things like transparency. letting your users know what's really happening with their data, or how this thing is working. Fairness. A lot of AI models are trained on most AI models are trained on real world models. Large language models tend to be trained on the internet. The internet is probably not a completely fair representation of the human species. So biases that humans might have might also um, persist in the model because that's what they're trained on. It's a machine, it's a computation, and their efforts uh, to bring out fairness, so make sure that fairness is there, and some other principles too. We're not going to go too deep into these, but just pointing out that these guide a lot of what happens in AI. And sometimes when you see AI behavior that doesn't seem to be working as you might expect it to, sometimes it's because the vendors are attempting to do things like instill fairness, and it's tricky, it's hard. So I think a well-known example, a well-intended example of this um, is models that were asked to, they were trained deliberately, or additional training, additional tuning to when they were asked to create images, to generate images that were more representative of the range of how humans look. Not just men, women, but different races and ages, various things. And there was a famous, well-known example of an image that was generated of the United States founding fathers, which, because of the era in the 1700s, it was mostly or entirely old white guys, and the founding fathers were more representative of the whole human race, but it was just inaccurate. So you can see the tension of trying to do things that are better for society, the intent, but sometimes the technical accuracy is very difficult to maintain in that context. Um, I'm not going to talk further about safety, but I want to point out that there's a whole set of ecosystems that have popped up to address this. And I just give two examples here. One is from Microsoft Azure. It's called Prompt Shields. And this is a layer of the tooling that you can apply within the Azure AI Foundry, which is their space to get AI models. We saw a screenshot a minute ago. And this is to help prevent, for example, jailbreaks. And a jailbreak in a AI sense is conceptually similar to a SQL injection attack, where you use a prompt to try to trick the LLM into revealing some information it shouldn't reveal, or taking an action its creator didn't want it to be able to take, try to explicitly tell it to not create it. And so a jailbreak might be to some early ones I recall are LLMs that have a system prompt, which is usually hidden from the end user. Uh, and then you have a user prompt. Those two get combined in the LLM. Where early jailbreaks, they could you could trick the LLM into telling you what its system prompt was, even though it wasn't supposed to do that. And then there's an effort for OWASP. We all remember the OWASP top 10 if you're a developer. And these are web vulnerabilities. SQL injection historically has been a big one, or cross-site scripting, stuff like that. And there's a list that's designed for the LLM that's being maintained by a pretty engaged team of people over in OWASP. I've spoken to some of them, and they're doing some good work there. So there's a top 10 list for LLMs there too. So I said LLMs are stateless. So how can a chatbot exist? Because what the intuition is, you go to a chatbot and you say, I want to plan my vacation in Cleveland, and what are some things I can do? And then the chatbot, ChatGPT or whatnot, returns like, here's a list of 5 things you can do in Cleveland. and then you might respond with, um, what are some good times of year to do the second one? So maybe it had a list of 5. And there's an implied context retention there where you expect it to know what the second one is because it gave you a list of 5. You expect it to pluck out the second, and you also expect it to know that we're talking about vacationing in Cleveland. Whereas if this was a Google search situation, you would have to restate all the context every time. And the simple answer is, how can chatbots exist? It's because it's all done in code. So if you're programming in if you were creating the web interface to ChatGPT using Semantic Kernel, you would have a chat history that you maintain as a programmer, and you send the whole thing as part of the prompt. We'll look at prompts in a little more detail, but prompts do a lot of work in LLMs, including all the history. So the chatbot illusion is that it is stateful for the user, but that statefulness is maintained in code, and the LLM itself is indeed stateless. They're non-deterministic. You get different results. If you ask for the top 5 things to do while vacationing in Cleveland, you will typically, if you run that 10 times, you'll get probably 10 different sets of responses. And even if the items to do are the same, the wording will be different. So LLMs are designed to be non-deterministic, meaning that you don't get exactly the same thing every time. That's a feature. And this is controlled by 2 parameters that you could pass in with a prompt. It's temperature and top P. We'll talk about those in slightly more detail later, but you basically have some control over how deterministic it is. We'll see that if you have various values of temperature and top P can make your LLM so non-deterministic that you get nonsense, and then there's a tuning process to come in where you get valuable responses that make sense. I'm not going to actually demo this, but as part of the semantic kernel set of tools, there's a agent framework that just went into release candidate 1. So that has that's finally coming to fruition. Parts of it are in release candidate 1. Then there's a less baked process framework that would sit above that. This might be the framework where you can have a human in the conversation with multiple agents, that kind of stuff. But if you run the unit test for the semantic kernel process framework, occasionally some of them fail, and then you rerun them and they work, which is a cute demonstration of the non-determinism, because the LLM doesn't give the same results every time. All right, very quick demo here. So we'll go to, come on. We'll go to simply ChatGPT, and this is slightly in bad taste, but it's a good demo. Tell me a joke about Hitler, and of course nobody really wants to hear a joke about Hitler, but I just basically want to show you its safety mechanism. Oh, so I have no idea what this means, but usually you get a different response. Let me just do this again. Wow, I've never seen it actually give me an answer. This is interesting. This is welcome to, I'm going to start the session
Could be
over.
the spelling. You put Hiltler. Hilter instead
Oh,
of Hitler.
that could do it. I got to learn how to type. Okay, thank you. Okay. Wow. Am I spelling it right now? I think I am. So I'm not really, so interestingly, okay, let me go to a different LLM here. I'll try, that was ChatGPT. This is Claude from Anthropic. There we go. This is more what I expect to see. And this is a safety feature. And this is a reasonable response. Like, we don't really want, if you're Anthropic, you really don't want people doing this kind of thing. It's not really worth supporting. And we go to Gemini, I think we'll get a similar response. This is Google Gemini, yeah. And these are great responses. These are appropriate. We don't really want jokes about that. Okay, but interesting that pretty sure ChatGPT. I don't think I've ever seen that from ChatGPT. I'm not sure why it's cooperative today. All right, so let's go back to PowerPoint. Okay, so we talked about LLMs, a little bit about safety and various features. Let's talk about tokens. You need to know two things about tokens. They're used in two different ways. I mentioned in the LLM section that a token is that the LLM is a token prediction machine. It produces one token at a time, and then it loops until it accomplishes whatever mission it has, and then it returns the value, which could be, the vacation tips for Cleveland, or the joke, or whatever you're looking for. So it's a prediction unit where the LLM produces the next token. Sometimes it's a syllable, sometimes it's a word. It might include punctuation, white space, or character return, anything like that. And we'll look at that forthwith. So that's one thing. It's a prediction unit. That's how the machine works, but it's also how you pay for the machine. So your prompt consumes a certain number of tokens that you pay for, and then there's some computation and an output, and you pay for those tokens as well. And here's some examples. We'll dig a little bit further into this. Maybe my Game of Thrones references are a little old here, but if you say winter is coming, and you ask the there's just one tokenizer, for example, but you ask platform openai.com tokenizer that we'll go to in a minute to process it and turn it into tokens. This is what you get. Winter is one token. Space IS is a second token, and space coming is a third token. So you see that it says it claims there are 3 tokens and 16 characters. Over here, it's 4 tokens and 17 characters on the right, because there's a new line in there. So a new line is a token, its own token in this case. But over here, it's a space is part of a word, or part of a token that contains characters. And if you do winter is coming in capitals, you get a different split. You get 5 tokens. Winter isn't one token anymore. Neither is space coming. And although is remains a token. And how do I know these are like this is and this is are the same token? Because behind the scenes, the tokens all have an identifier. And you can see the is 382, and it's 382 everywhere. Winter is 170,000, and so capital W is 90,000, and all caps is 47,000. So so this is the an example of the LLM decomposing text into tokens. Just for another example, you can see Boston. When I capitalize it, it's space Boston is one token, but when I use lowercase, it's a different set of tokens. It's space B and then Austin, OSTON. And the point being, or the intuition here is that when the large language model was trained on the internet, Wikipedia, everything, it saw a huge number of references to the word Boston with a capital B, because that's the normal spelling, and very few with no doubt that there are references on the internet that say lowercase Boston, but there were just so many fewer that it didn't get its own token. just like WINTER, all caps didn't get its own token. So this is the concept of a token. And the token count I mentioned matters for a couple of reasons. One being that's what you pay for. So if your prompt is, in a single run-on sentence, introduce a famous programmer, and we'll look at that in the tokenizer in a second. This claims that there were 19 prompt tokens. That's claiming that if we put this in the same machine that yielded these things, we should get a value of 19. And then there were 43 completion tokens and if you add these two numbers up, you get 62. So how many tokens did I pay for with this interaction? That was 62. That's how much. They're a tiny, tiny fraction of a penny, but that's how you can do the math on what it costs you. All right, so let's go back into demo mode, and there we go. So this is the text from the slide that we saw. That there's some debugging output that showed that says 12 tokens. So if we delete the period, it goes to 11 tokens. But this confirms that this is 12 tokens, input tokens. And if you want to see those token IDs, you can switch the view here. That's all it is. This is the underlying embedding model that we'll talk further about as we build our understanding of how LLMs are put together. But these are the IDs that are used internally to represent these tokens. And you can go here and play around. You don't need to log in or anything. Azure Cleveland, 2 tokens. If I change that to a capital D, we're up to 5 tokens because there's no idea what to do. There is nobody at volume when you're training has a capital D at the end of Cleveland. Do the same thing there. If you create nonsense, it doesn't know what to do with it either, and so forth. But it tokenizes everything you throw at it.
Question, Bill.
Yes, sir.
What if you were to use a previous phrase, let's say Azure Cleveland user group, and just capitalize words in the middle or capitalize letters in the middle? Would it still recognize them as individual tokens?
What's your prediction?
I would say yes.
Once it's in territory, in which we've thrown it in here by just making one capital E, say, in the middle, once it's in territory where its training data, the internet, doesn't really have this represented well, it's going to go to the multi-token situation.
I see. Makes sense. Okay. Thank you.
You're welcome. And we can also back off to, there are other models here that don't necessarily share the same. So see, this is 7 and 16. We go here at 6 and 16. So the number of tokens from this older tokenizer that was associated with GPT-3 yields a different, they changed something about how it was trained because the underlying token breakdown is different. Let's see, what are we seeing that's different here? So Azure space C, Azure. So Azure is 2 words in the older version, but it's one single token in the new version. Interesting. So the point there being that the tokenization strategy has to align with the language model that you're using. So if you went to the Facebook Llama model or this Anthropic Claude model, say, that there's no guarantee that these tokens are done in the same way. It's the same idea, but if it was trained on differently or with different data or different weightings, different emphasis, the model comes out non-identical. Actually, let's try one more thing before we move on. So this is Google Translate, and we have the word river here. So let me try that in the tokenizer. $21,842. 14. So it's a different token. It's the same semantic meaning, or close anyway. I don't know how. So we go to Telugu, and this is 2 tokens. So just pointing out, we're going to look at vectors in embeddings shortly, and there's some portability in the embeddings and the vectors, but it isn't inherited by the tokens. So if you translate languages, there's no reason to expect that the token is the same. This is a very different glyph for even than than river. But just pointing that out, that'll hopefully be a useful observation in a couple of minutes. Okay, let's move on to embeddings. When we looked at the screenshot for what I call the model as a service for Azure AI Foundry, we saw that there were a bunch of different models available for you to pick, including ChatGPT 4.0 and ChatGPT 4 Turbo, and some different kinds of text to speech and image, text to image. One of the examples in there was for an embedding model, and this is a popular embedding model that came out of OpenAI actually in about a year ago. So the important thing here is an embedding model takes your tokens. So the tokenizer that we just saw that breaks a phrase up into tokens is then handed to an embedding model. The tokens are handed to an embedding model, and that turns that sequence of tokens into a vector that represents the meaning of the tokens. We're going to focus on text here, but it could also apply to a video or image or audio and so forth. So I'm going to hang here for a minute and emphasize this. Let's see. So when I say meaning, I mean meaning. If you have a phrase talking about dogs and cats, that has some, we all kind of intuitively know what that means. And that's what is being expressed in these vectors. So you could take a sequence of numbers, a vector, and the AI makes draws meaning from that. Like, just, it's pretty hard to it's hard to understate that. So I'm trying to emphasize that point. So many of you probably have heard of the rise of vector databases in this past 5 years or something. They've become pretty popular. And a vector database is a database that uses this sort of embedding model, like text embedding 3 large. And there are various techniques. The most popular one is called cosine similarity analysis, which does vector math. And it compares how close the meaning of two vectors are. So if you have puppy and baby dog as two separate phrases, they get turned into tokens with the tokenizer, and then those tokens get turned into vectors, which is a bunch of numbers. And then cosine similarity analysis can say that they are not that far apart, puppy and little baby dog. And then if you maybe compared puppy to ice cube, cosine similarity analysis would hopefully say that those are further apart than puppy and baby dog. So this is just mind blowing if it's the first time you're seeing this, but you can actually do this analysis by meaning. You can ask, because the LLM trained on the whole internet, and the embedding model was trained on the internet, and it can actually do the math on how close our two concepts are. And this doesn't have to be just one word or some tiny thing. It could be there are limits, but it could be a paragraph or a page or various things. And the size of the vector that is supported by text embedding 3 large is 3072 dimensions. So you can think of that as an array of 3000 floats for the developers out there. This side note is interesting. So if you want to make 3072 floats, and if you're a vector database and you're comparing a lot of meanings with each other, you have a lot of data in there. You might want to make a trade-off, and you might only want to store something less than 3000 floats per embedding, and trade off some space versus accuracy. And it turns out not all embedding models are like this. I think most embedding models are not like this, which is if you truncate from, say, 3072 to 2000, and you take them off the end, you do a true truncation, it's still the least relevant bits are at the end. So a subset of the vector can still be used to express the meaning. You just lose a little precision. And in fact, Microsoft has Azure SQL Database now supports vector storage, so you can use it as you can create an embedding model using an embedding model. You can create a vector and store that in Azure SQL DB. But the limitation of Azure SQL DB is that it only supports 256 dimension vectors. So it's making that trade-off here, saying, well, we're not going to go all the way up to 3000 plus. We're going to stop at 256. And that works pretty well. There's some benchmarks that show that it works pretty well. So interesting characteristic of vectors and vector databases, especially around this fairly recent model, embedding model. Okay. So now let's do a demo to take a look at this. But first, I'm going to try to help develop a little bit of intuition about this. So imagine an analog clock, and an analog clock has an hour hand. First, well, I guess there's an imperfection in an analog clock. Usually when we talk about vectors, we want to normalize them. So we'd want the hour hand to be the same size as the minute hand and the second hand, say. So you can imagine, assume that, maybe they're different colors, so you can tell them apart. But imagine that that if it was 5 minutes past midnight, you can imagine the two hands fairly close to each other. That might be what the representation is for baby dog and puppy. They're pretty close. And maybe something like 1220 or 1230 might be a better representation of, might be a reasonable representation of, say, baby dog and ice cube. They really don't have much to do with each other, so they're kind of, they're a little bit apart. And that's a two-dimensional vector that I'm describing there. That would be if we had two integers, two floating point numbers. But I said that it supports up to 3,000 dimensions, 3,000 floating point numbers. So if you add a third dimension, then you can imagine maybe the second hand is coming out of the clock. So that's another way of differentiating itself from ice cube, baby dog, and puppy. And then if we add a fourth dimension, it's harder to, as humans, we don't really have a way to visualize this. But if I'm remembering my good example from college calculus was, well, you can imagine the fourth dimension could be the temperature at that, where that vector is. So that's a fourth dimension. And then maybe a fifth dimension could be the time that the measure was taken. But pretty quickly, you run out of ways of thinking about and getting your head wrapped around what a multi-dimensional vector is when you start to get to dozens and then hundreds and then thousands of dimensions. But the reality is you take that two-dimensional clock or the three-dimensional clock with the second hand sticking out, or where the hands can also stick out from the second dimension, and then you add all these other dimensions. That's what a vector is. So good luck visualizing it. If you have a better way than me of doing it, I'd love to hear about it. But they can have thousands of dimensions. So let's look at we're not going to attempt to visualize that beyond the clock, but I do want to show a demo here. So this demo is, so let me bring up this code. This is a console app. It's written with Semantic Kernel, and it uses embeddings. And it's using, in this case, an OpenAI. It's using the embedding I mentioned in the slide, the one from about a year ago, text embedding 3 large. And you can see I was playing around there. There are others you can use. And I've written some code that does cosine similarity analysis between two, mostly they're words, but sometimes they're phrases. And if we look at cosine, let's see the semantic compare. So the cosine similarity is it's a vector math. I'm not gonna talk about it. I'm not even gonna show it. But basically, you can look it up. But it's basically vector math from college physics or something. And I create a bar chart here. So I'll make all this code available. It all is available, but I'll give you a link that shows you where to find it all. And go back to program here. So this is the cosine similarity analysis between these things. So when I run this code, I just do .NET run. And this bar chart is, if it filled all the way up, that would be a complete match, or very close to a complete match. This is dog and cat are match at almost 0.6. 0 means that they don't match at all. Doesn't mean opposite, but it means there's nothing in common. Opposite doesn't mean what you think it means here, because like dog and cat actually have a lot semantically in common. They're little, they're domestic animals in one use of it. They also can have other meanings besides the furry little animal you might have at home. You can see some of these get pretty close. Pablo Picasso with lowercase Pablo Picasso gets pretty close, but not haven't hit 9 yet. And if we want things that are pretty opposite, arithmetic and coal miner, that was, or not opposite, I would be careful. Things that aren't semantically close, arithmetic and coal miner, that's pretty low. I think that's the lowest one showing up the top there. This I don't know why this is in the middle, but then I was trying to get some that were further apart than arithmetic and coal miner. So I tried some junk and tablecloth, banana, nucleophysics, pretty good with crayon and nucleophysics. But I couldn't get one that was below 1. Um, toilet paper sheet, nucleophysics. I did finally do it. I'll show you how I did it. But let me, so it's a spoiler here. The only way I could get 1 is the identity comparison. I took the same word and I compared it with itself. So that came out 1 as expected. But so do people understand what's going on here? I run the cosine similarity analysis with this 3,000 dimension vector and ask it how conceptually similar these two items are. And it tells me hiking and jogging, or hike and jogging, are 0.42. Hiking versus jogging is a little bit better. And then I also, I glossed over it when I flashed the code up here, but I also added the ability to do expressions. And this is an important thing with vectors. They're vectors, so you can actually do arithmetic on them. So if I compare hiking versus jogging, so this expression says take the vector for hiking, take the vector for woods, and subtract the woods vector from the hiking vector, and then compare that with the jogging vector. That didn't come out very, like I might have expected those to be closer, but that's what the math says. Um, um, here's one you might see in like white papers about embeddings. Queen versus king minus man plus woman is 0.52. Queen versus king plus woman, it gets a little closer. Extremely happy versus utterly devastated. There's no computation there. Anyway, so that's what vectors. This is a visualization of how close these various vectors come out. And then the question is, I couldn't get any that were less than 1. Actually, I couldn't get any that were negative. Pretty hard to do. And I actually figured it out. I ended up, let's go false, and that's going to run a different branch of this code. So let me go back here and run that. And it's going to show you some big messy thing. Any of you English majors, you might recognize the output here. So this thing here, this one, I add some extra characters in there to highlight it, but this is this one here. I got a negative value. Very hard to do. This is, anybody recognize this? So this is Beowulf, which is an ancient, English text, some of the earliest English text, versus nucleophysics. So that if I compared those with cosine similarity analysis and that particular large embedding model, I got actual negative closeness. Negative values are allowed, but they're just hard to come by. So I had to use Beowulf. All right. This code is in here, cranking vectors. Now let's go to prompts. Three more concepts: prompts, tools, and agents. I have 4 sons. I coached a lot of sports when they're all grown now, but when they were kids, I coached a lot. And one of my oldest son was in like he was 5 years old or something. He played what's called around here at least called T-ball, and you hit off a tee. This is an AI generated image. That's not my son. And so you hit off a tee. And it was one of my first coaching experiences. And the experienced coaches told me that, yeah, the biggest problem we have with these kids is no matter how many times we tell them not to throw the bat, they throw the bat. And so I realized after some point that uh, if I didn't tell them that, I told them to put the bat on home plate instead of don't throw the bat. They did that. Sometimes like they'd whack the ball and then they'd stop and they'd gently place it on home plate and then run like heck to first base. So I bring up this true story because it's an early example in my life of prompt engineering. Um, Prompt engineering is rephrasing things or giving more detail or changing the emphasis so that you get better results out of the LLM. So yeah, this is pre-AI prompt engineering. This is a few years back. So in prompting, a prompt tells the LLM what to do. I mentioned earlier that there are different kinds of prompts. I'm not going to get too much into that here. I just to mention it for emphasis though, there's a system prompt, and that's usually hidden from the user. That might do things um, uh, uh, like tell it what not to do. Like you might have an experience that is only about some narrow focus, and maybe like with this, usually in the like if somebody asks you about the book I, Robot, maybe you have a system prompt that says you are a helpful assistant that helps people with science fiction books, and then you ask it about a calculus book. In your system prompt, you can tell it to respond to non-science fiction prompts with something like, well, I only really know about science fiction. So if you want to know about, calculus, you're on your own. So there's a system prompt and there's a user prompt. Sometimes you also have a persona or, like you're in that can mix that. But point being, there are multiple, the prompt is an additive commodity. It could be text, media, or other forms. So you can, if you haven't done this, you with some of the web-based or mobile-based LLMs, you can actually paste in an image, and it will use that as part of the prompt. A prompt can include extra grounding or contextual data. So this is how chat works. So that's extra contextual data. It can also, so it mentions RAG here. RAG is an acronym that you'll encounter a lot in AI today. It stands for Retrieval Augmented Generation, and the augmented part means that you actually looked up some other data and included it in the prompt. And how do you find data that's relevant for your prompt? Probably, well, sometimes at least with a vector database. So if the user is asking about iRobot, and you did a semantic comparison using cosine similarity analysis and embedding in an embedding model vector, it might find that iRobot is pretty close vector-wise, similarity-wise, to say Isaac Asimov, who's the author. So a vector search might find that. An old school, text-based search wouldn't find that because the text doesn't match. And we'll talk about functions shortly. I'm going to quickly go through this. A lot of details here, but I'm just trying to give you the flow. So this is the prompts journey. This is your software, or this is maybe the web browser interface to your LLM for your chatbot. And then here's the hosted part. But you can think about this as your application. If you're building something, you're integrating an LLM with, say, Semantic Kernel. So there's a path here where it works its way into the hosted LLM, and then it works its way back, and you get a response. So I just want to dig into the details of that very briefly. So yeah, this is probably running an Azure AI Forge. It could also be an LLM, an SLM running on your laptop or on your phone or something. That's the route. And let's zoom in on these sections one at a time. Let's go to this one. That's the zoom. So you send your prompt, could be text, could have an image, etc. It might be a system prompt, which I've talked about. It might be more than one. And then some like implementation context, like an API key, the model, whatever you called the model in AI Forge, AI Foundry rather, and then these temperature and top V values that we'll talk about in a minute, and the token budget. You can tell how many tokens you're willing to spend on this, so it's not open-ended. So it checks your API key. It checks that you're not rate limited. You're not hammering it. There's a prompt safety check that it does. You can also augment that with what I talked about earlier with the protection for prompt injection, prompt shield. That's a service that you can buckle on to your hosted LLM. And then in addition to API requests, there's a tokens throttle. And then there's a context window size check. So context window is there are limits to how big the LLM can be, how big the input to the LLM can be. It's kind of, you could think about that as we could be having a conversation about, I don't know, maybe we're doing a design of a software system, and a couple of us are in this conversation. We're all trying to keep a bunch of stuff in our head, and the stuff that we have to keep in our head is the question that we're trying to answer, and then the solutions that we're coming up with. Combined, those make up the context window, in the analogy with the LLM. Okay, so I'm going to zoom into a different part of the diagram. Here we hit the context window. There's an accounting done. So you sent in 25 tokens or something, or maybe it was 2,000 tokens because you have a big chat conversation that you're sending back in at a whole, or maybe there's more tokens because there's an image and so forth. But that accounting is done because that's what you pay for. Stuff is vectorized. Stuff is sent to the LLM of your choice, and then there's a loop as it chews through your request. Remember, it's a next token generator, and it keeps going. It sums up all the tokens it generated one at a time and returns them as a response. It applies temperature and top P. These are variable. These are values that you provide, parameters that you provide that tell it how creative to be or how much variability there should be on repeat calls. You might think of it as. Then there's a response. It might be a response. There is a response safety check. More accounting because you used more tokens. And let's go to the last section here. Then a response goes out, and it might include text, it might include images, and it also includes token usage. I showed a screenshot earlier that showed the total token usage. It's the total of input and total of output tokens. So how do you influence the prompt execution? The context of the prompt. So prompt engineering. Oh, I think it's the next slide, actually, not the prior one. Or it's a couple slides away. Yeah, I'll come to that in a second. The chat history. So it remembers that we were talking about vacationing in Cleveland. So that's sent back in as part of the prompt. Retrieval augmented generation. This might be a lookup in a vector database, so that it also has some information about Isaac Asimov, because I asked about iRobot, one of his stories, or it looks up something. We'll get into this more in the agent side. You might want to give it access to your customer ticket database or your financials database, depending on what this is, right? So you have the power to give more information to the LLM. So you can look up stuff, look up Isaac Asimov. You can scoop up some, who the customer is who's asking this question. So maybe you scoop up that person's tech support history, and you pass it in as part of the prompt. These are all up to you. You know, the prompt can do a lot of work. And then there are token probabilities in the model, and we'll get to that in just a second. Max token is something you can specify. You know, I only want to use 3,000 tokens here, and that will cause the LLM to give you a more concise answer. And we talked about the context window. That's what it can keep in its head. So I'm going to come back to that. Okay, I'm going to come back to that in a second. I want to talk about prompt engineering. Prompt engineering is a general term that is all about how do we make the LLM do what we want it to do, you know, get better results. And these are like official industry, you know, official, probably the wrong word, but these are established terms in the AI industry for various strategies for prompting. So zero-shot prompt is examples. You know, how old is the president of the U.S.? Translate river into Mandarin. Translate, I think that's river in Telugu, I think, into Mandarin. These are one-shotters, and they're easy to answer typically. But if you asked a really complex question zero shot. If you ask a really complex question as a zero shot, you might not get nearly as good results. So, for example, maybe I want to go on a vacation in Cleveland, and there's a certain time of year I want to go, or or I want the output in a certain format that matches a JSON structure so that I can further programmatically process it. A zero shot wouldn't be appropriate there. A one or a few shot might be appropriate, where I give it some examples of what I want the JSON to look like, for example. And I'm not going to go through all these, but just I wanted you to get the point that there are various approaches that you can read about that other people have thought through and had success with in creating prompts that give you better results. Let me go back to this guy. So I talked about top P and temperature, and here we'll finally get to them. So there are, when you the LLM is a next token generator. There's a pool of tokens that are eligible to be the next token. One is the most likely, and then some are less likely. And so we say hello or hi or the candidate words. Let me bring in this. So the next token, these probabilities were determined by the model based on the training of the internet. So you ask a question about vacationing in Cleveland, or these aren't the appropriate answers for that, but the next token might be hello with probability 0.4 and hi with probability 0.3. And these probabilities, this is the whole set of tokens. So these probabilities have to add up to 1.0, because that's how probabilities work. And what happens is like was up. It's like a much less formal or common, but not zero probability response. That's kind of equivalent to hello. And if you want to limit the number of options, you can do that with top P. So with top P, I can say, just give me those that are in the top 0.7. And if you do that, that's just the first two, hello and hi, because you'll see those probabilities add up to 0.7. So that would exclude hey and below. So if I say top P equals 0.7, if I say top P equals 1, it includes them all. And it could be certainly more than 6. It could be 100 or various numbers of possible candidate next words, next token. I say words here, but it's really token based. That's a simplification. Then after top P is considered, like if we do top P equals 0.7, and that means we're limiting to just these two, we can say temperature is this says 0.25, and that's a reasonable so a temperature of 1 is pretty common, or temperature of zero point 0.7 is common. It doesn't work the same way as top P, but this smooths out the probability of the ones that are left after top P. So a bigger T smooths them out more. A smaller T smooths them out less. T goes between 0 and 2 typically. Top P between 0 and 1. So a top P, a T of greater than 1, like a T of 1.5, would make these two probably indistinguishable from each other. A T of 0.25 gives more emphasis on, okay, this is a little more likely. Still make this one possible. Don't always choose this one, but bring this into the fold some of the time. So I'm sorry, I don't think I'm doing a good job of expressing the intuition around this, but top P is a lot clearer. That's a hard cutoff. Then T temperature smooths out the other probabilities. If we had top P equals 1, and we included all these, the top P of 0.25 would probably make was up a little more likely than 1 in 100. And whereas a T of like 1.0 or 1.5 would make it, I don't know, I'm going to pick a number, say, make it 1 in 10. It'd be only half as unlikely as all the others. So it smooths out the probabilities. I'm not going to demo this, but I just want to tell you about it. There's a pretty cool plugin for VS Code called Prompty, and you can learn about it here. But it's another way of building. It's another tool for you to. It's a tool for you to manage prompts, and like I said, I'm not going to demo it, but it's a tool through which you can execute a prompt to test it out against an LLM, and and the format is a YML file, a YAML file, and it can be loaded. You can load a prompt from disk from a Prompty file in Semantic Kernel. It's a supported configuration, so it's worth looking at if you're building coding a solution. So let's get to tools and agents. Tools is a big turning point here in our journey. Sometimes also called plugins or functions or skills. A tool is what the title of this talk is about. Is let's give our AI some tools and give it a goal, and then let it do its work. That's where it starts to turn into an agent. But let's talk about the tool part before we talk about the agent part. Examples of tools that we can give our LLM is this is becoming less of a problem or less of a thing you have to do, but LLMs, generally speaking, don't know what time it is. So if you ask it the weather, it doesn't know what time the weather it should get is, and it also doesn't know where you are. So asking an LLM to tell you the weather is a bit of a challenge. So there are tools that you can provide programmatically, declare for your AI that are things like telling it what time it is. Something super basic. You may also want some domain operations. Is prime, calculate a mortgage payment for maybe you're a loan shop, and you don't want the LLM itself to figure out how to do these things. You want to give it the tool to do that. Maybe you have a specific mortgage calculation that you want done, not whatever it thinks up, because it will think up a way to do that if you don't tell it how to do it. And just this is just a recent. This is with Google Gemini. Google's calendar trash folder only keeps deleted events for 30 days. Since I was asking you about something related to the Google Calendar trash, and since Bill, your stuff has been in the trash for 10 days, they're likely permanently deleted because it's exceeded the 30 days. So this is pointing out that they're not always great at math, because 30 is greater than 10, not less than 10. So it inverted this logic. So its math is not always to be trusted. And what they used to do is they used to do math in the LLM. Now they typically generate code, execute the code, and use those results. So it's a little, they've upped their game because LLMs are good at languages, not math. Another tool you can give it is access to Bing or Google. So the LLMs were all trained at one point on the state of the internet on some day. And then they were trained for, how many months it took, but it still started on that same day. Say September of 2023. There might be LLMs that are, that's their epoch date. But if you want more up-to-date info, you can use RAG, you can use web search. These are various tools available to you to bring more information into the fold. So this can be however up to date the internet is. You can also give it access to your company's systems, private systems. These are internal systems. It might be able to read inventory of files, or if a customer is on the line, trying to look up their order history, say, you can give the LLM tools to look up the state of their order. And these can be traditional services. It might just, if it knows what the user's, email address is, it might just look up the user and then return, the list of support requests, say, or orders in this case, and not, it doesn't have to be anything fancy. Or it can be vectorized stuff because they might have a particular question, and then you might do a vector-related search on, to sort it out more sophisticated way. And this is a pretty big deal. They can also do updates. You might have your LLM, give it a tool that it can create a support ticket. So we're almost at agent here, where your agent can do stuff. I'll skip these. These are conversation questions. So I mentioned, you give it tools like search the web. For example, this is the pretty basic. You need a key, an API key, but basically this is how you add it to Semantic Kernel. Make it available for dependency injection into anybody that needs a Bing search feature, a function. And this is created by Microsoft. This is an off-the-shelf. You just have to ask for it. You can also write your own. We'll look at when we get to the agent in a minute. There's one that describes an image as a URL, and this one here is a URL validator. Is this URL really a valid URL? This describe image at URL one is code that will be invoked by the LLM, and the invocation returns a description. So you pass it the URL of an image, and it returns you a description of that image. And inside that describe image as should say as URL, describe image as URL function, it because it's just code, it happens to actually use a different LLM to do the work. So I believe in this code example that we'll look at in a minute, it uses OpenAI directly, whereas the LLM that is calling the function is Azure OpenAI. So two different instances of LLMs. So you can have stuff that is already built for you. You can build your own, and it's code, so it can do anything code can do, including invoke a different LLM, hit the internet, hit your database, create a support ticket. And then there are ones that are actual prompts. This is a prompt, like a prompty file. This represents a prompt. This is the Semantic Kernel calls these prompt functions or semantic functions. And then there are other ways of doing things. There are other formats and so forth for managing prompts. You can even do them in code if you want, right in your C# code. You can hit any endpoint that has OpenAI API Swagger 2.0 colloquially, but OpenAPI is supported, so you can do things over the network. And again, this is just code, so it can do anything that code can do. And then model context protocol is another emerging protocol for LLMs calling tools and functions. So let's get to the end here. What makes an agent? It has agency. It can do stuff. So you give it a goal, you give it a task or an assignment, and it can go and do things. Maybe it has memory, some state. Chat is a good example of that. It definitely has tools like the functions we were just talking about. Calculate a mortgage payment, open a sport ticket, and so forth. And you give it a goal in the prompt. So I've created a fairly simple agent, and yeah, this is the semantic kernel line that distinguishes an agent. It gives it agentic powers. This is saying go off on your own and start calling functions and let me know when you've reached the goal, as opposed to just responding to a particular chat. And I'll show you that. So this will be the last part. I'm going to run what I call an icon agent, and suppose you're creating an HTML page and you want to mention Java or Python or something, and you want its logo, but you also want to support um, the users who don't have who can't see, say. So you want to support accessibility features. So you want a description of what the logo looks like. So let's go do that. So icon agent, I run it, and it's going to say, please, what do you want me to create a logo for? And let me run this on, let's do it on the GNU project. There's a lot of logging in here, and you'll have access to this source code. So it's calling this endpoint GPT-4o in Azure, and blah, blah, blah. A lot of this is OTel OpenTelemetry. And these funny characters, I use different characters to call attention to the different functions that it's using. So it's using Bing to try to find a logo, and it got a logo from its Bing search, and it tried to resolve it. You'd be surprised, maybe you wouldn't be, but how many times you get, example.com/logo.bing, it really isn't a file. And then it more debugging, so you know which function this is. And then image depicts the head of a GNU, which is also known as a wildebeest, which is a stylized and cartoonish, so you figure that out. And then we swing all the way down to the end. This is my HTML. So, or actually it's right at the end here. So this is what I could paste into my website that supports accessibility. The image depicts it, so you see that. It's got an alt tag that is the GNU logo, and a reference that it's validated it actually resolves and is a ping file. So let's do it one more time with, say, Python. So let's see, validating this URL. So it worked. Okay, so what it's not showing here, because it's succeeding on finding the URL in the first try, is what happens if it finds a URL that isn't working. Let's do C++. So it found some that weren't actual logos. You saw the X's there. And then I've told it to retry. And let's go to the bottom. Did it finish? Yeah, it never found a C++ logo. But it didn't give us a bad answer either. It didn't say, hey, here it is, just because I found a URL. And let's do one final thing. Let's glance at that code. So that's a chat app that we'll skip, but the like the image describer function, this is its logging, and this is it's basically a C# function method with this attribute on the top that this is what the LLM sees it as, and it sees this description, and it makes sure the URL isn't empty, and gets an LLM here. It gets the Azure OpenAI one directly, and calls the LLM, describe what is depicted in this image, and passes it the URL, and that's his answer, and that gets returned to the LLM. And there's a prompty file. This is what a prompty file looks like. This is basically, these are comments. This is a YML format, but API keys from the environment. And these are commented out because I experiment a lot, but you can try what it's like to get the Python. And I could actually run this right here, I think. And it's you can look at some debugging info, token use, and so it found a logo for Python. All right, let me. I'll make all the code available. It's already out there. I'll share some stuff with Sam to find it. And let me see how do I get to my slides. All right. Any questions or any confusions? Anything you want to talk about before we wrap?
There were no questions in chat, excuse me, but there was some dialogue. However, if anyone has any questions now, feel free to come off of mute.
Anything worth reacting to in the dialogue? Let me find I'm not used to this app. Let's see.
There were some links that were shared, but no questions specifically.
Okay.
All right, and it looks like we have no questions. So, thank you, Bill.
Okay, thanks for the invite, Sam. Thanks for having me. And
absolutely, it was very informative, and you covered a lot of ground there.
Okay.
And as far as the PowerPoint and the slide deck, will you be able to share that with us?
I will. I'll send you a note within a couple of days, Sam, with a link to find everything.
Yeah, absolutely. Sounds great. I just got a couple wrap-up announcements before we adjourn for the evening. So if you don't mind, I'd like to go ahead and share my screen.
Right on.
All right, so if you take a look over in the chat window, you'll see that there's 3 links that I posted there, and we'll go over those. Basically, first link is for the YouTube channel, where the recording will be posted in just a couple days, right after the editing process. If you would please subscribe to that to get upload notifications. In addition, a link to my blog, where I post technical events, Q&As. Whenever I get a slide deck from Bill, I'll also post a link to that there as well. And if you would please subscribe to that to get the updates as well. And last but certainly not least is the link to the feedback eval form. This way we can provide Bill with some constructive criticism. If you're in the job market, feel free to check out devitjobs.com. It's a great website that allows you to search on the type of technology you want to be using, the geographical region, whether you're working remotely or in person. So all these are various filters that are available on the website, and it's free of charge. My contact information, should you have any questions, my email is snasser My email is snasser@nistechnologies.com. You can also find all my social links for the blog and YouTube channel, tree/Sam Nasser. And lastly, if we're not connected on LinkedIn, let's do so. It's a great way to keep in touch and connect with others, and you can find me there as well. So, with that, thanks again to Bill for a great presentation, and thank you all for attending, and see you all next month. Good night, everyone.